All righty. So I looked at my email, and the email I got says they're looking at Thursdays, July 9 through August 13th. That's tentative, you know. Plus, there's some stuff we're going to have to do, like they're going to be looking at us to make sure everything gets wiped down and stuff like that. So, you know, I'm going to have to get some clarification on things. What exactly are they looking for us to do? Anything and everything we touch, you know, that's going to be challenging. I'm also interested to know, you know, who else is going to be in the building. Is it like, because sometimes they have 100 people, you know, when we were going before, there was like 100 people there on any night we were there. And even under the new phase 4, that's like 50 too many. And that, so we'll have to find out what the protocol is about face masks and all of that fun stuff. And hey, there it is. All right, you made it. Oh. All right, can you hear me, Chilo?
Yeah.
All right, good. So I was just telling them, and I'm glad you made it. I'm recording this, so if you missed it or you want to review it, we can go back. But info that I got about the hands-on, tentatively, is July 9 through July 13. So that's 5 or 6 Thursdays. I think 5, because I think this is 5. So it's going to be on Thursdays, starting July 9 and then on August 13. It's tentative. Now I'm going to have to get some clarification and find out for sure, because that email was beginning of June, you know, a little while ago. So I got to make sure if they're changing anything, because the governor changed, you know, kind of opened up to phase 4 for Friday. And I got to figure out what that means. Do we have to wear masks, gloves? What? I don't know. I don't know all those details yet. So I'll work on that and let you guys know. But I wanted to give you a heads up. That's tentatively what I was told. So so I got a few of you turned in programs, and I made some comments and sent them back to you. Did you get that?
Yeah.
Okay. All right. Good. So you know, I'm trying to squeeze some programming in, because that's usually, you know, where you want to try and get to. And if you write it, it helps you to understand it and, you know, and read it in a program. If you don't end up getting through all of the programming, you know, it's not like this is a class where you're getting a grade. So as long as you're, you know, trying to learn something and you come away with learning something, then as far as I'm concerned, that works, you know. Again, if you always, anytime you got questions, you can shoot me a text or whatever. I posted some documents on Edmodo. So let me share my screen. Well, first of all, does anybody have any questions before we roll? Okay, so let me share my screen. I'm thinking it's this one. Edmodo. Are you able to see the Edmodo class?
Yeah.
Okay. So what I did was, you know, we're going to start out. We're going to talk about cutter compensation, ramp on, ramp off. I saw a couple of things, and I want to clarify in 1 or 2 programs. We didn't actually ramp off, and you need to have a X or a Y move when you ramp off to really disengage the cutter compensation. So that's why I say ramp on like the expressway and ramp off. So I made a smaller piece PDF for cutter compensation instead of having to hunt through the whole Haas manual to find it. Also can cycles, we're going to talk about that, you know, drill cycles, tap cycle. We'll talk about that tonight. I got some info on taps, and then a setup sheet, because what I'd like us to do is program the holes. That'd be the next step. If you've programmed the outside shape, it'd be to program the holes. So that's kind of the game plan. let's see, I think I have to stop sharing, which doesn't make sense to me to share again. And it is this one. All right, do you see a print with some code on it now?
Mm-hmm.
Okay, good. All right, so this is in that cutter compensation document. And this is an example of the cutter compensation. Come on. So when we turn it on, this line N6, G41, that's cutter compensation left. They have an X move. So they're over here where it says start, and they go straight across. And then that's when it turns it on. Notice the feed rate. A feed rate has to have a decimal point at the end because the feed rate's calculated in what's considered a 2-4 format. No, it's leading zero suppression, which means I don't have to put any leading zeros. So if I have nothing but F12, it thinks it's going at 1 2/10 thousandths of an inch per minute. You're never going anywhere, at least not today. So you got to make sure you have a decimal point. A couple of programs didn't have decimal points here and there. It's just a habit. You know, if all of a sudden you see it's going really slow, look for a decimal point missing. So here, line 7, then they cruise around up, they go around. If we come around to line 9, which is where they're coming back, then line 10 here is where they're turning off cutter compensation and they make an X move and XY move. So they're coming off farther and turning it off. So I just want you to be aware you do need to ramp it. It says down here, tool diameter must be entered in the offset. The control will position the tool. No, that's not the one. Somewhere I saw a note that said something about a move. Which one was it? Needing an X move. Needs an X or Y move in order to truly shut off, especially if you're going to do multiple depths. I'm going to go around one time. Let's say the block is really thick. I'm going to rough it out in a couple of steps. I'm going to go down a ½ inch, then I'm going to go down a ½ inch. You can use the same program, but you have to come off cutter compensation, go back to your start point, ramp back on cutter compensation every time. Otherwise, it's going to give you a problem. Oh, I didn't know he was in the waiting room. Oh. Let's see. Okay, you're back with us? Okay.
Yeah, I lost audio and my internet connection was, I think, going down. So
Okay. Well, no, it was good because it popped up on my screen that said you were in the waiting room.
okay, yeah, because
So
I ended up just leaving and then reloading my
now
browser.
sometimes that's the only way to go, but I have you guys like, do you see pictures of you guys on the side of my screen, or do you just see the white screen?
I see pictures.
You do. Okay.
Yeah.
So when I see that, I don't really know, and it doesn't tell me who's in the waiting room. So at any rate, the main thing I was trying to say was you need to make sure you have an X or a Y or an X, Y, and Y move on that G40 line to make sure that it cancels it out. So that's my main pitch reminder about the cutter compensation. So if you're ever having trouble getting it to work on the machine, out in the shop, look at, do you have enough room of a ramp to handle that diameter cutter? Do you have a diameter or radius, depending on the machine, as an offset in the offset? And did you cutter compensation the right way? Okay. Any questions on cutter compensation? Kind of makes sense. it's really once you get the hang of it and you kind of treat it the same way all the time, it's usually fine. It's definitely better than programming without. Now, I will say that a lot of times on a CAM software, you have the option to choose whether you want it to be compensated in the control or in the computer. And if you choose in the computer, it automatically like shifts it based on the diameter of the tool you put in, and then it puts out those numbers based on that shift. The downside to that is it doesn't really turn on cutter compensation. And like I said, if I had a 1-inch end mill, I broke it, and all I have is resharpens now, my part's never going to be the right size unless I go back and fix it because it doesn't have cutter comp. So I recommend cutter compensation all the time. But if your company does something different, then you go with that. All right, so let's talk about CAN cycles. So we're drilling, tapping, boring. Those are G81 through G86 are the most common ones. G80 cancels it. And it really makes your life a whole lot easier. So basically, you're going to position in X and Y. Looks like I was having a seizure there. I was like, you're going to position above, and then you're going to come down. So typically, once you make a tool change, you want to make it a habit to position up above before you call out the G81 or G82 or G84, whatever you're going to do. So let me know if you guys are, if I'm cutting out or my video is going wacky, because in the little screen I see the video going a little bit crazy, and I don't know if it's my signal or if it's something else. Okay, so if you're not getting it, let me know. All right, so according to this, we're going to position in XY, this number 1. Then number 2, we're going to wrap it down to the R plane, R for rapid, and then we're going to drill, tap, or bore, and that's going to be executed by whatever Z we put in, Z minus 1 inch or whatever. And so it's going to do the hole, it's going to go down to the bottom, and then it's going to retract back to the R plane. There's 2 R's. Let me see if I can get this to work. Really? Let's see if I can. It worked earlier. No, that's just dandy. All right. I guess it doesn't work on when I'm recording. So what I wanted to show you was there's G99 and G98. So when it comes out of the hole, depending on if I use the G99 or a G98, and if you look at your book, I believe G98 is the default code with the asterisk. So when it comes out of the hole, it's either going to go to the R plane, which normally you have like 100 thousandths above the part, or it's going to go to the initial plane. So in this example here, line 15, G81, so it's a drill cycle. It's going to rapid to the R plane, which is R 100 thousandths. It's going to then feed at 6.5 inches a minute down to minus ½ inch. And when it gets down there, it's going to rapid back up to this R plane. If this was a G98, it would go to wherever my initial plane is. And so let me see if they have an example on that. Page 2 has a list of what happens when you pick that. G81 feeds in, end of hole, nothing happens, it just rapids out. So this kind of breaks down the parts of the CAN cycle. G80 cancels it. I'm looking for G98. Oh, here we go. Here's a good example. So G98 Now, G98 and G99 are modal. So they stay that way until you change it. So if you don't put one or the other in there and the default's G98, and when I come down, that initial plane is the first Z. So look at line 4. When you come down to length offset, turn on H15, so it's offset 15, 1 inch above. So the initial start point is 1 inch. That means if you have a G98, like there is on line 8, when it comes out of the hole, it's going to go to 1 inch above the part. Okay. If you look at the picture down here in the corner, my screen doesn't get blocked. There's a clamp here, and you can't always go around the clamps, especially if you remember when you're going from hole to hole, it's going at a rapid. So that means it's going at a 45-degree angle until it satisfies one of them. So if I was going from the upper left-hand corner to the lower right-hand corner, it's going to go on a 45 until it satisfies one of them. So, you know, to think that I can go from this picture of hole 1 to hole 7 or something like that, it's probably going to clip the clamp. So I would use the G98 so that I could jump the clamp. Okay. So as a rule of thumb, whenever you program, I highly recommend when you pick up your tool length offset on the G43 line that you use 1 inch as your Z instead of 100 thousandths. What happens is it rapids to 1 inch, and even if I was drilling a hole right away, which it is right here, it is then going to rapid to the R plane at 100 above the part. So you're not going to be feeding from that 1 inch above the part. So it's not like you're going to be wasting a lot of time, but it does set things up so that if I need to jump clamps or something like that, you can work around it. Another thing is sometimes you have a pocket and you have to put holes in the bottom of the pocket. Okay. You might want to use the G98, that initial point above the part, but your R plane might be negative inside that part. So I wrap it down, I feed in, I drill a hole, and it comes back up completely out of the part before it moves to the next hole. There's a lot of different scenarios where G98, G99 comes into handy. But it all gets set up by this first Z move when you turn on the G43. Are we good? Make sense? Okay. So once you're in a can cycle, G83 through G89, I believe it is, whatever, 86 are the most commons, 81 through 86. Every X move or Y move or XY move is going to execute the same can cycle that you initiated until you come down like line 13 and give it a G80 to cancel it. So that means it's drilling a hole here, 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 here. Notice they changed from G99 to G98. And they numbered these in this example. So N6, line N6 is hole number 2, then the hole number 3, then they went to hole number 4, so that when it comes out of hole number 4, right here, when it comes out of the hole, it's going to go up to the initial plane, which is 1 inch. So that G99, G98's when it comes out of the hole. Okay, not going in, when it comes out. So on hole number 4 here, get out of the way. When it comes up out of the hole, it's going to go to 1 inch above, so that when it goes to the next hole, which they made a G99, it's going to, at that 1 inch above, it's going to go to hole 5. It's going to wrap it down to the R. It's going to drill the hole, and it's going to come back up to the G99, which is the R plane. So it's not going to be up in the air. It's going to be close to the part, close to the part, close to the part, all the way around. So that's how you can use this G98, G99 to control. I'll be honest with you, a lot of times you're only doing G99 because you want to keep it close. So you set that once, but if you make it a habit to having it, the initial plane being 1 inch, then if something comes up and someone decides they got to add a clamp here, you just got to add a G98 to the line and change that, and everything's happy. Make sense? Good?
Mm-hmm.
Okay. So are you guys familiar with how the G codes work, the different G codes work? It's actually kind of like multiple steps all put together in like a little routine. Okay. So if we look at this one, so line 2, they positioned at rapid to x plus 5, y minus 5. So that's where they're putting this hole. Yeah, this hole. They turn on the spindle, they wrap it down, pick up the offset with the G43 to 1 inch above. They decide to use G99 on all the holes because it's all down. It drills a hole there, even though there's not an XY on this line, okay? Sometimes if you're writing manually, or even on CAM software, a lot of times it'll respit out this X and Y position again on the line because it pulls it. That's just the way that it's written. You don't have to, because it's already at that position when you turned it on, but all the rest of them, every position, it's going to drill a hole. So if we look at this, let me see if I can make it bigger. If we look at this drill, here it's using the G81, it's a drill cycle, so that's just a straight down. So it's going to the initial plane, which is 1 inch above. It's going to then rapid to the R plane, and then it's going to feed to the Z minus, then it's going to rapid back up. So in these pictures, when you look at them, the dash lines are for rapid, and the solid line is for feed. Okay, so if you're looking at any of these later, that should help you out. So it's rapiding over an X. This one, it's rapiding down to the R plane, feeding down to the bottom of the hole, and rapiding back up to the R plane. So each one of these CAN cycles, they have a little picture like this. G82 is a spot drill, which is basically just like a drill, G81, except there's a P. And that P is time at the bottom of the hole, okay? So in this example, line 5, N5, G82, spot drill, it's at the rapid plane, it's going down. When it gets to Z minus 375, it's gonna dwell for 0.5 seconds. It says a dwell up here is in seconds / milliseconds. So it's a half a second, it's gonna sit there and it's just gonna spin. Okay. Then it's going to come out of the hole and go and do the next hole. And again, they kind of show us the same thing. When you get to the G83, it can be simple or you could make it complicated if you'd like. Which, if I'm drilling, let's say I'm doing a mold and I got a water jacket and I got a really long hole, you know, that's 5-6 inches deep or something like that, I might use some of this extra stuff. So normally you're positioning with X and Y. My Z is my final distance. My R is my rapid plane. My F is my feed rate. I can put a dwell in here so that when it gets to the bottom of each peck, it'll stay there. Usually I find that just makes chatter, which I don't want. Q is the peck, equal increments, if I'm not using I, J, and K. So most of the time I'm just using a Q, and whatever my Q is, like 0.1, 100 thousandths, every 100 thousandths in Z, it's gonna wrap it back out of the hole, it's gonna wrap it back in just short, and it's gonna feed down another 100, wrap it out, wrap back in, feed some more. I'll show you the picture in the middle. The more complicated version is if you add this I can make my first peck bigger, and then J, I can make it less each time after that. Okay, so as I get way deeper in the hole, I got way more stuff packing up on my flutes. Okay, so I may only, as I get really deep, I may only want a 50 thousandths peck, but when I'm first starting out, I may want a 200 thousandths peck. So that's where you would get into that, those different type things. So here's a kind of a picture of how it works with just a normal XY, going to the R plane and using Q. So here's Q. So it rapids, it feeds down the depth of Q, it rapids back up, it rapids back down just short of the hole. And over here it notes that this is setting 22. So in your control, there's a setting page, and there's a number that's in there. There's a factory default setting. You can go in and change it, but that says how far is it going to stop before it gets to the bottom of where it left off drilling on that last peck. Okay, it might be 10 thousandths or 20 thousandths or maybe 50 thousandths. I don't know. It kind of depends. But that's just so that it kind of doesn't smash into it. If you were doing a small drill, you'd end up breaking your drill. Okay, so each peck is going to go down to the whatever the Q number is. It's going to wrap it all the way out of the hole, wrap it all the way back in, just short of the last where it left off, feed, wrap it all the way back up. So that's peck drilling. Sometimes they call it deep hole drilling. There might be another option on your control that's called chip breaking, where it just kind of almost like pauses. It's like e, 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 e. It doesn't come all the way out of the hole. It just kind of pauses and keeps going down. Chip breaking. Sometimes that's fine if you're not going really deep and you're just kind of blasting, roughing out a hole. That works fairly decent. Okay, so I mainly want you to be thinking about using the Q when you drill. So in our drilling exercises, don't go crazy unless you feel like you want to experiment with it. If you write the program in the NC viewer, excuse me, NC viewer, it's not going to show you any Z. It really doesn't show you much, but you could look at it on your computers at work possibly. So I would just worry about doing a Q. And question?
Yeah.
Yes.
When you do packing, you have to use the G83, right, instead of G81?
Correct. Correct. So G83 is the peck drilling, and you have to have a Q.
Okay. Yeah, yeah.
So you're going to still have your R, you're still going to have your Z, you're still going to have your feed rate, XY position, and then you need to have the Q. And kind of a normal size is like 100 thousandths, depends,
Okay.
you know. And it's easy to adjust because oftentimes, let's see if they do it. Let's go back up here. Oh, we should go down that up. In the code, the G83 line here, number 5, they got a Q of 0.5, so a ½ inch. But notice they don't have a Q on the next line. It's modal, which means it stays that way until you tell it a different number. Even to the next tool. The next tool, you call up a G83 again, it's still going to remember that Q unless you change it. Okay? So the nice thing about that for this tool is, let's say I had 10 holes, but I only put the Q in line 1, this first line, and I go and figure out, holy cow, a ½ inch, no way, that's not going to work. The chips are way too big, they're flying all over, coolant's not getting in the hole, I need that to be smaller. You only have to go to this one place and change it. Whereas if you put a Q on every line, you'd have to change it every time. Does that make sense? You'd have to change it on every one. Now, let's say I got a couple of short holes and then I have a long hole, okay? And you may want the Q to be a little bit longer on the short holes, but when you go to a long hole, you may want the Q to be shorter so that it breaks the chip better. So let's say this next hole is longer. You can just change the Q, add a Q, Q.1 on this other line. You know, it's flexible like that. Are we okay with G83? Makes sense?
Yeah.
Yeah. If you want to get into this other stuff, I'll let you go look into it. It's a little bit more complicated. You're going to have to read through it. But for the nuts and bolts about what we normally do, the G83 with the Q works very well. Okay. Tapping. Let's see if I can minimize you guys. So tapping works the same way as far as an X, a Y, an R, a rapid plane, a Z, and a feed. This J is kind of, I've never used J. I'll be perfectly honest with you. Okay, the tapping retract speed. So there's two kinds of, let me say, tapping modes on your machine. One, it has, let me stop sharing this for a second, just because. Okay, so there's two kind of tap holders. There's two kinds of tapping. There's tension compression, which is I'll use my water bottle maybe, try. Here's my tap, okay? So there's a spring in here. And so as I'm drilling and tapping the hole, its spring can extend or it can push in, okay? The reason then it was set up, old machines are that way because they are not as accurate about their feed rate, okay? So if it's not a perfect match in the feed rate, let's say I'm feeding too slow, it would pull the tap out a little bit instead of breaking it, okay? And when I come back out of the hole, I know I'm going the wrong way. When I come out of the hole, sometimes it goes a little bit faster and it stretches the spring. And when it comes out of the hole, you'll see it snap. I don't know if you guys have that. Have you got that?
Yeah.
Okay. So that's like because you don't have perfectly matched RPM with the feed rate. Okay. On the newer machines, they're a little bit better, especially if you buy the option. It's called rigid tapping. And in rigid tapping, I could put my tap in a collet and it perfectly matches the RPM and the feed rate. Down, stop, back out. Doesn't break the tap, okay? But if you don't have rigid tapping, you got to use that extension compression holder where it's got that spring in it. Okay, otherwise you'll be breaking taps all day long. Okay, so most of the newer machines, you know, if you're getting a new machine, tell them you want rigid tapping. It's well worth the money because I can tap a whole lot faster. So I could go at maybe 50 inches a minute instead of only 10 inches a minute because when I go faster, that spring pulls and I break my little taps all the time, you know. So that's kind of a little bit of info on the rigid tapping. So let me go back to sharing on the tapping here. So the way that tapping works is you call it up the same way as any other one. G84, you got the choice of the G99 or G98. I have my Z, I have my rapid plane. Oftentimes, kind of a rule of thumb that I've always done is, especially if I'm going at a fairly fast feed rate, is my R might be 0.2, 200 thousandths above, just a little bit extra room to get in and to get out, okay? However it works for you guys, that's fine. Now you have to calculate the feed rate regardless of the tapping cycle. And so the way that it works is 1 divided by the threads per inch. So I have a 1/4 20 tap. I would take 1 divided by 20. In that case, that gives me, if I do my math right, should be 0.05. Then I take that 0.05 times the RPM, and that will tell me what my inches per minute feed rate is. I'm kind of lazy. I don't want to make a mistake, especially when I've been all this time in a part. So if I'm programming it at the machine, I'm going to pick something nice and easy, like quarter 20 tap, 20 inches a minute. I'll go 200 RPM, 10 inches a minute. So I like to kind of go at 10 inches a minute, but you might have a really weird number like this F35.7143. You can't throw away the decimal and go with just F35. You'll break your tap, okay? So this is a formula that you're gonna wanna know. 1 divided by the threads per inch times the RPM, that's gonna give you your inches per minute feed rate, okay? So when this works, when this goes, you don't need, well, I always put a M03 anyways, but what this is saying is G84 automatically is going to select M03. I would get in the habit of always putting M03 whenever I turn on the spindle, or M04 if I happen to be going backwards, just to make sure that I never forget it, because the last thing I want to do is try and drill or mill without a rotating spindle. Okay.
Would you be getting your RPM from like the machinist handbook?
Yeah, so yes. So I would probably look at something for tapping, and you know, it might say, okay, I got a high-speed steel tap, 200 surface feet. I'd figure out as a quarter inch, 200 surface feet. Then I would, you know, do the 1 divided by threads per inch times that RPM. Now, in every machine, there's a maximum feed rate you can go. And it depends on the machine. As far as what that is, you know, it might be 30 inches a minute. I don't remember offhand if there's a standard number. But yeah, either that, or you're going to go from the tap manufacturer. You know, if it's an OSG plug tap, you're going to go and look at OSG, and they're going to tell you what they recommend.
Okay.
One of those two sources would be the ones to get that info. You know, it kind of depends on your tap too, and I have a document that I've shared, and we'll go look at after this, about the different types of taps, because it makes a difference, because you have to determine how deep this tap is to go. So if I'm let's say I'm drilling a hole a ½ inch deep, and I want, well, let's say I want 3/8 thread. Depending on the type of tap, I might have to make that hole like 3/4 of an inch deep. And if I can't go that deep because of the parts specs, then I might have to get a bottoming type tap, or a little to no lead on the tap, and I'll explain that better in the next document. But when you're tapping and when you're drilling the hole to be tapped, you need to know, hey, how many threads do I need? I need a ½ inch of full threads. Then I have to calculate what my lead is, and then calculate some room, because most normal plug taps, they're going to push the chips into the bottom of the hole. So if it's a blind hole that doesn't go through your part, those chips are going to pack up at the bottom. So you're going to want to leave some extra room. If I can, I would drill deeper. You know, if my part's 1.5 inches thick and I want a ½ inch of full threads, I figure, oh, I need 300 thousandths for the lead. That's 800. I need some room. I'm probably going to drill my hole 1 inch deep, maybe 1.1, just so that I have no issues. Okay. And that's kind of a game you'll have to play, to get a feel. And your company might kind of have a rule of thumb. Hey, we always go a ½ inch deeper. You know, I don't know. It kind of depends on your company. So how this really works is this tap is going clockwise, G03, to the XY position. Then it's going to wrap it to the R, can you see my little arrow guy?
Yeah.
Okay, good. And then it's going to spiral down. So it's going to spin and move down in Z until it gets to the bottom of the hole, okay, to the Z. It's going to then stop the spindle and then reverse it to M04 and spiral its way back out to the R plane. And then it's going to change the spindle back to M03. So, couple of things. When I'm tapping a hole, it's going to do, if I put it on single cycle, it's going to, it might have to push cycle start a couple of times because it might move to the XY position. I might have to press cycle start again, and then it matches the RPM, and then I press it again and it spindles, it goes down and it stops at the bottom of the hole, like it thinks that's the end of the block. And it'll sit there. It's not spinning, so it's not a problem. Hit cycle start and it will retract back out and then reverse the direction. So depending on the machine, it might break it up into several little chunks, that one little cycle. Does that make sense?
Mm-hmm.
Okay.
Yeah.
So kind of depends on the machine, but one thing that's kind of nice about it is if you do it on single cycle as your first, proving out a program, it stops and you can kind of get an eyeball and say, hey, look, I'm almost burying those threads all the way up to the top of the shank. You might have a problem coming up, you might be okay this time, but if you have that tension compression type holder and it pulls it out farther, you're for sure going to break the tap. So that's kind of a nice thing about when you're proving it out by going by single block. One other thing, once you execute this G84 command, feed hold does not work. Feed hold, feed override, spindle override doesn't work. So let's say I've been running my spindle at 150% and my feed rate at 50% because my programmer doesn't know what he's doing, whatever. Okay, so I'm not at 100%. When it comes to tapping, it's automatically going to use the numbers that are in the program, even if you really want it to be different. It locks those out. You can't override the spindle or the feed rate in the tapping mode, which sometimes is really good because if you've been playing with the speeds and feeds and forgot to change them, it would for sure break a tap. G74 for left-handed taps, same thing, same process. There's a couple of different options for boring. Here's one, it's bore in, bore out. So it's going to bore in, same thing as a drill, X, a Z, an F, an R, okay? It's going to feed all the way down, and then it's going to feed all the way back up. So it's going to bore itself in, bore itself out at the feed rate. G86, what's going to happen? Oh, this is still the G85. It feeds in, feeds all the way out. G86, it bores in, stops, rapids out. Sometimes, if you cut it again with zero tool pressure, it sometimes does weird stuff, depending on the material. Other times, maybe if you got a super hard material, you may want to bore in and bore out to make sure that there's no tool deflection. That's a preference or an experiment. So those are the main ones. Like I said, there's a few other boring options, and they're in your book, and you can look at them. They're also in the full-blown Haas manual that I gave a few weeks ago. It's up there. And that class, I'm not taking that stuff down. So even after our class is done here, you'll be able to go and get that stuff. So, but I would pull it down as PDFs and save it so you don't have to go there anymore. Anyways, it's less convenient. So, questions on CAN cycles? Okay, so let's look at some of this technical info for taps. Let me see if I can make this big enough to actually see. All right, so there's a number of different types of taps. So there's a bottoming tap, the chamfer on the bottom here, or the lead, they say is 1 to 2 threads. A second tap has 3 to 5 threads. Tapered tap has 7 to 10 threads that are lead. So if you look at this, it's kind of hard to see maybe, but those aren't full threads. So what they're saying is the first, in this particular one, 7 to 10 threads aren't going to make full threads. So if I were to screw a thread of screw into that hole, that screw is going to stop somewhere here. It's not going to make it down to here. It's going to get closer to the bottom on this one. So sometimes you're going to tap a hole with something like this, a plug tap, a regular standard tap that has a bunch of lead like this. And then you're going to hand tap it off onto the side because you got to get down to the bottom and you don't want to risk busting a tap. Now these are hand taps. Machine taps work kind of the same way. We've got a spiral point or a plug tap. Does it tell us how many threads? I don't see it. I think in the machinist handbook or in, let me see real quick on the Haas. Oh, remember when we were talking about threading with the G84 on tapping? And I said that it's 1 divided by threads per inch times the RPM. If you're doing, so 1 divided by threads per inch, let's take the 1/4 20 tap, 1 divided by 20 is 0.05. That's the pitch. On a metric tap, I have M5 by 0.8. The 0.8 is my pitch. So I would just take that 0.8 times the RPMs. I wouldn't do the 1 divided by, because a metric tap is the pitch, not threads per inch. Forgot to mention that before. So that's noteworthy. I thought that maybe in our little book they had something about the lead of a tap. But I don't see that. So I'm going to say you're going to have to refer to one of 2 methods. Hunt through your 2,500-page book that's not that easy to find stuff in, or you go out to the shop with your dial caliper and you measure the length of the of the lead yourself, and then go, oh, it's about 300 thousandths. Okay. But so up here we got a plug tap, spiral plug tap. This here, this spiral fluted tap. These are really nice for non-ferrous materials. It's a fast spiral. Note there's very little lead. So on this one up here, the spiral point, this is spiral flute. This spiral point tap up here, the normal, you might call it a plug tap, okay? This is the one that chips are gonna go down in the hole, inside the hole. This is the most common one used. This spiral flute tap, these things are awesome, but more expensive. But the chips come out like little strings, and they come up like little wires coming up, but they don't go in the hole. So if I'm doing aluminum, something like that, I can really crank with this, and I don't have to worry about chips. Very nice tap. And then, I don't know, do you guys do roll form tapping? Roll taps?
Mm-mm.
Okay, so this one, different size, definitely if you have to roll thread. So a lot of times, so basically the difference is this roll thread, this type of tap, a roll forming tap, it doesn't make chips because it doesn't cut material. It pretty much just forms it and moves it into the shape. So for aluminum, this is a much stronger thread than a regular cut thread because it still has all the material. It's just been displaced, kind of like knurling almost. Okay. But you got to have different size drills that affect this. But roll thread taps are useful. Long taps, they're the same thing, same different types. They're just longer. Pipe taps, so you could have a straight pipe tap. You could have a tapered pipe tap. They could have different coatings, like these in the pictures, like a nitrite coating. So depending on the material, you might want a certain kind of coating on it so that like aluminum doesn't stick to it and build up and cause problems in your threading. Titanium nitrite coating, kind of the same thing. Oh, here's some info about RPM or tapping speeds to be calculated, surface feet per minute. Oh, here's a little bit of, here you go. So here's, I don't know whose chart this is, to be honest with you, but here's some examples of surface feet per minute for the different type of material. Some troubleshooting, some tap terminology. I'll let you guys study it when you're interested in it. Metric tap size. So there's some tap charts tied with this too, which I had forgot about. So, okay. All right. Questions on taps?
That's a nice handout.
Yeah, that's not too bad. There was more in there than I thought. See, I thought it was just this, so I must have gone and found some more stuff and put it together. I have a tendency of doing that. Maybe not, but yeah, I like this one. There's a good amount of information.
Really well.
Yeah, there's some decent information in here. So that's free. All right, so if we look at this, so most of you or many of you program this outside shape. If you didn't do that, you might want to work on that. What I would like us to do this week is to drill and tap these holes. If you get that done, you might want to slot this out. And we'll talk about that in a minute. So these holes are listed over here in the chart over on the side. So typically, one way or another, you should be making some sort of a setup sheet. Plain, you know, whether it be just a list of tools on a piece of paper like we did on the lathe, or if we make something official. If you're a programmer, you should come up with something that's kind of formalized and consistent so that, you know, your operators can kind of get to knowing where to look for information, so that they're not losing a lot of time on the floor trying to figure out what the heck you're doing. Okay. So this is one Titans of CNC has this, so I downloaded it, I modified it to use with my students at school, so I just took my school logo off of here and did it for us. So the reason I did this is because if we're milling, let's mill with the 1/2-inch end mill around the outside. We're going to use a 1/2-90 spot drill. Anytime you can, use a 90-degree spot drill. And the reason you want to do that is because whatever diameter you want, the Z is half that amount. So if I got a 250 hole that I'm drilling, you really should be making a spot so that there's a countersink so I don't have to deburr it later. I don't like to work more than I have to. So I'm going to program that to maybe be 280 diameter. So my Z is going to be half of that, 140 deep. If I use an 82-degree spot drill or something else, then you're going to want to consult your little Haas handbook and find out how to figure out that distance. But with a 90-degree spot drill, it's really nice and easy. The Z is half of the diameter I want. Okay, so that's why I said 1/2-inch spot drill. We're going to use a 5/16 drill. Now, I'm going to be honest with you. In reality, if you look at these tolerances, hole A, 312 plus or minus 2,000s, I'm sorry, but you're not drilling that with a drill blasting in there one time plus or minus 2,000s tolerance on the diameter. Okay, that's probably a reamed hole. Okay, same thing with the 281. But for our purposes of programming, I want you to use a PEC drill, G83, to drill these holes. Okay, and just drill them. Now, I want to tell you, since I mentioned ream, so let's say I drill this hole, I would probably drill it somewhere around 300, something like that, whatever size that would be. And then I would ream it. Now, if I ream it, I would use a G81 cycle to ream it. Drill in, rapid back out. Okay. When you ream a hole, since you want it to be round and you want it to be smooth and consistent size, so you're using a reamer to kind of true up a hole and make it hold tight tolerance and size, you're going to go with a lower surface feet and a higher feed rate, because you actually want it to go in and cut and come out. You don't want it to just rub. You want to make sure that reamer's not wobbling, because if the reamer's wobbling, it's going to cut oversize. So that's my suggestions on that. If you get all the holes done and you're going great and having a good time, what I would like you to do then is do this slot. Okay. Now, if you look at this slot, it has some tight tolerances. Are you guys familiar with geometric dimensioning and tolerancing at all? GD&T?
A little bit.
Like this stuff that's on this print. Let me make it a little bit bigger here. Like, do you know why these dimensions are in a box? And not all of them are. So here's one that's not in a box. So I'll touch on this a little bit. GDT is like a whole nother language. Okay, so we look at our print. I have tolerances down here in the bottom. This is my tolerance. 2 places to the right of the decimals, plus or minus 10 thousandths. 3 places to the right of the decimals, plus or minus 3 thousandths. Okay, so this 45 right here, 0.45, is plus or minus 10. Over on the left over here, there's 0.300s, plus or minus 3. If a dimension is in a box, that means it's a basic dimension, which means these tolerances don't apply. So basically, it's saying those tolerances are modified. So I have to look at the whole call out over here to get my tolerance. Okay. Usually it's making the tolerance smaller or connected to some restrictions. Now, you guys are aware of the A and the C and stuff like that on the side of the part. Yes?
Mm-hmm.
Datums. So this is datum A, or surface A. Datum C, datum E, datum B. So this particular hole up here, and it says all holes, so all holes are held to this tolerance. So this circle with a plus sign is true position. I think I gave you a handout a week or two ago that has some of these basic GDT symbols in it. But anyways, this means true position in a diametrical tolerance of 6. That's like plus or minus 3, but it's in a circle. So compared to a square, if you laid a circle from the same center point +3, -3, like this hole is a circle. But now if I did a square, +3, -3, I would have a little corner up here on a square. Do you follow me?
Mm-hmm.
Okay. So if I have a diametrical tolerance, I lose that corner. So I can't be x +3, y +3 from my hole center and still be in tolerance. So it makes the tolerance smaller. It kind of takes away that little corner that I used to be able to have under these tolerances. Okay. So anytime you got a dimension in a box, it's a basic dimension and it's going to be governed by something that calls it out somewhere. Okay. So here, over here on the right, this perpendicular, so datum B is perpendicular within 5 thousandths to A. So I have to go and look. So this side has to be perpendicular to the top within 5. So you've probably seen parallel and perpendicular callouts quite frequently. It's just some of these other ones you don't always see. Now, just going to mention this. We're not going to get into it, but this little M in a circle, that's called maximum material condition. So if I have a hole, this hole A has a ±2 tolerance. On that hole, what size would the hole be if there was maximum material in the hole?
310.
310. Smaller. So when, why can't I move? Okay. When I am at 310 diameter, I have 6 thousandths. When I'm bigger, 312 or 314, you have a different amount of tolerance. I think they call it bonus tolerance. I don't want to, that's a whole nother world I really don't want to get us into. In fact, I was taking a class totally on GD&T. It's overwhelming. And TMA, by the way, if you need to get into that, I know TMA every now and then runs a GD&T class on like Saturdays, 2-3 Saturdays every now and then. But anyways, so I just wanted to mention that about some of this stuff because, you know, a print like this can be overwhelming. Especially, you know, if you don't understand these things, it's going to be hard to make it in tolerance and not get rejected from inspection. So this little slot is the 187.5 radius, so that's a 3/8 diameter. So theoretically, I could cut that with a 375 cutter. Have you guys ever run? Now this thing's going to go a 1/2 inch deep into the part. Even if I take multiple steps, how straight and nice do you think that would be if I used a 3/8 cutter to cut that slot? Do you think it would be straight and in tolerance? Think about tool pressure. Have you ever noticed when you cut full diameter of the cutter that it kind of walks off one way or the other? Yes? Have you guys noticed that at all? It will. So in this particular slot, you really can't go full-size cutter. You got to go with the smaller cutter. Okay? And since in this particular case, I have a really close tolerance, this is the profile of a surface. That's the whole surface up and down and all around. Has to be within 6 thousandths to A and E and D. To this end, and A, I think, is the bottom, or the top surface, sorry. So it's kind of ridiculous, to be honest with you. I think it's pretty ridiculous. This is the part my students have to make to get NIM certified on the CNC, okay? But so the way to make this slot, or anytime you're going to want to go with a smaller one, you can rough it and then come back and do cutter compensation. Does that make sense? That way, if the tool deflects a little bit, I can clean it up when I come around after the fact. So in this particular slot, I would say that you need to go in with 5/16 end mill. I wouldn't want to go smaller, because I would, if I go with a quarter, that's pretty small diameter for the depth. And it's going to be a lot of deflection. It's going to move a lot on me, maybe even break. So here's what I would suggest for that. Let me unshare so I can show you something else. I've never tried this before, but let's see. Now supposedly I can write. Not sure how. Spotlight. Draw. Okay.
Oh, no.
Sorry about this. It's pretty crummy looking. If this is a slot I was trying to machine and I wanted it to look really nice, I could come in with a cutter right at the center, a smaller one, and go straight up, then go down a little bit farther, come back, go down a little bit farther. So I could do it back and forth in a couple of steps. Okay. Now I've roughed it out. If I'm using that 5/16 cutter and its finished size is 375, that leaves me 1/16 total, or 30 on the one side, 30 on the other side. Okay. So that's perfect. I could come in here, drive around the outside with cutter compensation, and it's a wonderful day. Except if I tried to bring my cutter, which is almost, oh gosh, that's terrible, sorry, almost as big as the slot, how can I ramp on? How can I ramp off? Because remember, it's got to move over enough to compensate to offset. So whether you use this here or you use this someplace else down the road, I want you to just kind of store this thought. There is nothing in the rules of cutter compensation that says I have to be in the part at my full depth when I invoke my cutter compensation ramp, when I turn it on. So every arc has a straight, so I would say my arc is supposed to go to here, then I have a straight line, then my arc. So these lines are like my change from straight line to arc, okay, because my drawing is so crummy, okay. So if I'm going to do cutter comp left, I need to be able to come from this side over here somewhere so that I can be on the left side of the line at this point. All right. So I can come up here above the part, 100 thousandths above the part, G41. Turn it on, G41's in place, puts me here, then feed my Z down. Then I can walk around this, back to this. I can feed out of the part, and then I can ramp off and my G40. Does that make sense? So I'm doing it up in the air, ramp, go into my part, cut my part, come out, cutter comp off. There's going to be some times where you just flat out don't have enough room to get the ramp, okay? And you might need to do that above the part, ramp on, ramp off, or ramp on, cut the part, come out of the part, ramp off. Does that make sense?
Yeah.
Okay.
Mhm.
Well, most of the time we don't think that way because we think, oh, I got to get in here. I got to be down inside here, and there's not enough room. Okay. So I'm going to get rid of that terrible representation of a. I didn't think about it until right when I was talking to you. Otherwise, I'd have drawn it up ahead of time like I did the other stuff, and it's much nicer looking. So at any rate, so that's kind of what I have going on for us to talk about in that. Does anybody have any questions on anything? Okay, so what I would like you to do is on the part that we programmed last week, if you didn't do the contouring and you need help, ask. If you did that, drill the holes. And if that comes pretty quick, which actually and honestly, if once you do one hole, you can, the meat and potatoes part of it, you can copy it and paste it, change your tool, your height offset, XY position, leave the rest the same. You're going to have to change your Z. But you know how you have the lines of going up to a tool change, the start and the spindle. That's kind of the same stuff. You can copy and paste that stuff. Okay. So that's what I want you to do is I want you to work on that as our assignment. And then turn it into me, and then I'll try and give you feedback so that you can look at it before class next week. Just trying to get us some programming. But at least, if working on the computer to try and do the programming doesn't work for you, spend a little time going through the documents, okay, and seeing if you can get a better handle on how the G81 works compared to the G83, or better understand cutter compensation with the documentation. Okay? So I'll stay on if you guys want to do some stuff and ask me questions, or you can go off and work on it, whichever works for you. All right?
Right.
And then I'll see you guys next week, whoever leaves.
Okay.
And I'm going to stop recording.